Okay, thanks very much. So I really appreciate the opportunity to be here. I really had an amazing 4 years in CTP, learned a lot, and really enjoyed my time here. So thanks a lot for the opportunity to be back. Today I would like to tell you about some work. I would like to speak kind of broadly about work in the problem of simulating quantum mechanics with quantum computers. And this is an area that I think has a lot of interesting connections between computer science and physics. So I want to talk about this problem really from sort of an algorithmic perspective, where we talk about the complexity of algorithms for solving this problem. But as I hope you'll see, there's some interesting interplay where we can use ideas from both physics and computer science to kind of inform this question, which then ultimately I hope will lead to devices that we can really use to do science, and I'll talk about that as well. Okay, so this idea of simulating quantum mechanics with quantum mechanical computers was really kind of the idea that led to quantum computing as a field. Sort of the idea that we could use computational devices to study physics was the thing that led to the idea of a quantum computer. And this happened in around the early 1980s when people like Feynman thought about this possibility. Feynman realized that it's difficult to simulate quantum mechanical systems with classical computers, basically because if you want to explicitly represent the quantum state, you need to write down a lot of information. And he thought, well, this is, in this quote, he says this is a wonderful problem because it doesn't look so easy. This was his perspective that he gave in what was a keynote speech at a conference at MIT, the Physics of Computation Conference in 1981. Okay, so we now understand a lot more about quantum simulation, but let me start by saying a little bit about why we might want to do this. Probably to many of you, it's kind of clear that we should want to do this, but there are many kind of applications where the ability to simulate quantum mechanics would be useful. So we might want to simulate quantum chemistry. So some reactions, in some chemical reactions, if the sort of quantum mechanics of the electrons in the system are really important, then that's going to be a difficult thing to simulate with classical computers, and maybe we can do it with quantum computers. Similarly, in condensed matter physics, or if we want to design materials, there are reasons why we might want to do quantum simulation, or even, and perhaps a little bit more relevant to some of the main themes of the CTP, if we want to do computational nuclear or particle physics. These are hard computational problems because of the large size of the Hilbert space that we need to simulate. There's also, as a sort of quantum computing person, there's a sort of another set of reasons to care about simulating quantum mechanics on quantum computers, which is not to simulate quantum mechanics for its own sake, but rather to use simulations of quantum mechanics as a tool for developing quantum algorithms. And many algorithms along these lines have been pioneered by people here at the CTP, including things like the idea of adiabatic optimization, algorithms that use quantum walks on graphs, and some more recent algorithms that basically do linear algebra in Hilbert space to solve linear algebra problems or related kinds of problems more efficiently. So there are lots of reasons why I think we might want to simulate quantum mechanics. So what I want to do in this talk is tell you about some algorithmic challenges that where we've sort of thought about questions about how efficiently we can simulate quantum mechanics on quantum computers. And I want to tell you about some of the ideas that went into solving those challenges. Not at a really technical level, but I want to try to give you some of the kind of high-level picture of what goes into these algorithmic improvements. Okay, so first, let's just talk about the idea of efficiently simulating quantum mechanics with a universal quantum computer. So this will maybe help to set the stage a little bit for what is the sense in which we think about solving this quantum simulation problem. So I want to think about the model of a universal quantum computer, which I'm not going to define in great mathematical detail, but just to say that this is basically a circuit model. So in a quantum computer, we have what are called qubits, quantum bits, that represent quantum information. And then we can manipulate those qubits using gates, which are described by unitary operators, which act on some small subset of the qubits. And then at the end of the day, if we want to get information out of the system, we can measure it. But the basic idea is that it's a circuit model. And what we're going to do to understand the difficulty of solving problems is we're going to quantify the work that goes into an algorithm in terms of the number of gates that appear in a circuit for executing that algorithm. Okay, so what is the quantum simulation problem? So this is really the problem of simulating the dynamics of a quantum system. So you have a quantum system which is described by a Hamiltonian. There's the Schrödinger equation, which explains how it evolves in time. And in the simulation problem, we're given some description of that Hamiltonian, a time that we would like to evolve for, and an initial state. And the goal is to produce the final state that you would get if you would evolve for that time under that Hamiltonian. And maybe we allow ourselves to make some mistakes at the end of the day, so we have some allowed error tolerance epsilon. And we would like to understand, for this problem, what is the complexity of solving of solving it as a function of things like the time we want to evolve for and the amount of error that we allow. Okay, so this problem is, as I mentioned, it has a lot of applications. You can, in principle, use it to develop quantum algorithms and to simulate quantum mechanics. But it's actually, in some sense, kind of the core of what quantum computers can do. This problem is formally, as hard as anything a quantum computer can do. In the jargon, we say this is a BQP complete problem. So this is a problem which really somehow captures the essence of quantum computing. All right, so how can we efficiently simulate quantum mechanics on a quantum computer? So, the sort of first kind of explicit algorithm for this problem was written down by Seth Lloyd, who's here at MIT, in the mid-90s. And his basic idea was the following. So imagine we have some Hamiltonian, which we can write as a sum of terms, each of which is individually easy to simulate. So, this could be some kind of a spin system where there's some local interactions. Maybe these are two-body terms on a lattice. It could be some more complicated system. But you can imagine that in general, if you have some reasonable Hamiltonian, you can write it in this way. So here's the main idea. So we have this Hamiltonian, which we can write as a sum of terms. So let's think about the simple case where we just have two terms. Now, these two terms are individually easy to simulate, but they don't commute. So you can't just simulate one and then simulate the other and then be done. But what you can do is the following. So you can simulate one of the terms, and then you can simulate the other one, but only for a short amount of time each, and then you go back and forth. And in the limit that you do this arbitrarily fast, then you're actually simulating the full Hamiltonian. So this is, mathematically, this is what's called the Lie product formula. And, Seth realized that you could use this idea to simulate quantum mechanics. And if you sort of, do the calculation that tells you how fast you have to alternate back and forth in order to have an accurate simulation, what you find is that if you want to evolve the system for time t to within precision epsilon, you need a number of elementary gates that scales like t squared over epsilon. So that's great because that's, we might call that a polynomial time algorithm for simulating the Hamiltonian. And we could use that, to give lots of quantum simulations. But now the kind of question that I want to get at in this talk is, we should never be satisfied with the complexity that we have. We should always try to do better. We always want to know, really, what is the fastest algorithm we could possibly have, and we want to have the best possible upper bound. So you can do better than this using this idea of higher order product formulas, where you have somehow a more sophisticated way of choosing how you go back and forth between the two terms. And doing this, you can get closer to an algorithm that has complexity which is linear in t, but with a prefactor that grows exponentially with the order of this formula that you use. So in practice, you actually can't get that close to linear in t. So we would like to understand, can we do better? OK. But actually, before I talk about doing better, I want to mention sort of doing simulation in a somewhat more general way, because this perspective will be useful for sort of thinking about the context in which we do quantum simulation. So the sort of kind of system that I talked about before is one where you have local terms in your Hamiltonian, but a sort of more general class of Hamiltonians you can think about simulating efficiently is ones that are sparse. So this is a model that was introduced by Aharonov and Tashma in 2003. So the idea is you have some Hamiltonian which is described by a matrix that has not too many non-zero entries in any given row. And let's imagine that we have the ability to, for any given row, find where the non-zero entries are and what are the corresponding values. So for example, we could query that particular row, and we have an efficient function that would tell us where the non-zero entries are and what are the values. OK. So there's a way of simulating such a Hamiltonian which works as follows. So it's based on edge coloring, a sort of problem of distributed edge coloring in a graph. We can imagine a graph where we have a vertex for every basis state that the Hamiltonian acts on, and an edge between two basis states if there's a non-zero matrix element in the Hamiltonian. And what we can do is try to color the edges of that graph. So for example, here's a much smaller graph than the one that would describe that Hamiltonian, but let's say we have this 5-vertex graph. We can color the edges, which means we want to assign colors in such a way that no two edges incident, if we consider a particular vertex, all of the edges incident on it have different colors. Right? So you'll see that this coloring that's written down here has that property. And if you color a graph in such a way, and then you look at the subgraph corresponding to the edges of a particular color, what you find is that the graph breaks into pieces where you have just isolated edges and maybe also isolated vertices. So these individual pieces are easy to simulate, and we can put them back together using the ideas that I mentioned on the previous slide. And since we can come up with these kind of colorings of the edges using only local information in an efficient way, this leads to efficient simulations of this more general class of Hamiltonians. So actually, for everything that I talk about in the rest of the talk, you can imagine this setting of sparse Hamiltonians. OK. So now let's get back to the question of really trying to optimize the complexity. So maybe one question we could ask is how efficiently can we simulate the dynamics of a quantum system as a function of the time that we want to evolve for, this parameter t that I described before. So it turns out that you can't do any better than linear in t. There's something that people sometimes refer to as the no fast forwarding theorem, which says that if you want to evolve a quantum system for time t, you need a number of gates that grows at least linearly in t. This is, I think, kind of intuitive that somehow, generically, you just shouldn't be able to fast forward the evolution of systems. If you want to get to the end of the evolution, you really have to sort of go through all of the evolution, and that takes a linear amount of work. And actually, the argument for showing this relies on a lower bound in quantum query complexity for a problem called computing parity. And actually, that lower bound was proven by researchers here in the CTP, among others. So we might ask then, can we saturate that lower bound? Can we get an algorithm which really has complexity that's linear in t? Well, as I mentioned before, we can use these higher order product formulas to get kind of closer to linear in t, but with this exponentially growing prefactor, so we can't actually get there. So we can ask, can we really do something which is linear in t? Can we give an algorithm with complexity that's precisely big O of t? And somehow, this ought to be possible because systems, are simulating their own dynamics in real time. I mean, if a system, evolves for time t, it only takes a time t to get there, right? So, somehow, if we have a computational model that really is universal and describes kind of systems in general, it seems like we ought to be able to do this. And it turns out that this is, in fact, possible. But there's a challenge. The thing that makes this sort of not totally easy is, I think, the mismatch between the Schrodinger dynamics that we're trying to simulate, which are really continuous time dynamics, and the quantum circuit model, which is fundamentally a discrete model of computation. So somehow we have to shoehorn this continuous time process into this discrete time computational model, and so we have to be a little bit careful about how we do that. But it is, in fact, possible, and a way of doing this is to introduce an operator called a discrete time quantum walk that corresponds to the Hamiltonian, which, because it's a discrete time process, it's discrete dynamics that are easy to implement in this circuit model. You can really implement it well in the model where we want to work. But it efficiently carries the sort of spectral information about the Hamiltonian that we need in order to give an efficient simulation. And so using using this idea, we can give an algorithm which has complexity which is linear in t, and if you look at the dependence on epsilon, it goes like 1 over the square root of epsilon. So it kind of solves this problem of understanding the dependence on t. Okay, but now maybe we should also understand the dependence on epsilon. What should we hope for, and can we do better than the complexity of the algorithms that we've seen so far? The complexities of the algorithms that we've seen so far are polynomial in 1 over epsilon. But actually, many approximate computations that we might want to do actually can be done with a cost that's polynomial in the log of 1 over epsilon, right? So exponentially better. So for example, if you want to compute numerical constants, like you want to compute the digits of pi, you can compute n digits of pi in time polynomial in n. So in terms of like how accurately you're approximating the value, that's polynomial in the log of 1 over the precision to which you compute that value. And more generally, there are lots of places in both classical and quantum computing where you can get you can solve some approximate problem with a complexity that goes like some polynomial in the log of 1 over the precision. So that's kind of the thing we would like to achieve. And now it turns out again that you can prove a lower bound, which shows that you can't hope to do any better than about log 1 over epsilon, specifically log 1 over epsilon over log 1 over epsilon. Again, using an argument which relates to the query complexity of parity, but now sort of the unbounded error query complexity of parity, the difficulty of computing parity with really only a small probability of success, only doing a little bit better than random guessing. But so what this shows us is that we really can't hope to do any better than log 1 over epsilon, but that's very far from the best algorithms that I've shown you so far. So can we do better? Can we get close to saturating this bound? So the quantum walk simulation that I described before has complexity that goes like 1 over the square root of epsilon. The product formula simulations that I mentioned before, these ideas where you go back and forth between different terms in the Hamiltonian, have complexity that goes like a better and better polynomial in 1 over epsilon, but with an exponentially growing prefactor again. So we really can't hope to go all the way to the limit where we have a really accurate, where we have something close to like log 1 over epsilon complexity. So again, the question is, can we do better? Okay, so it turns out that, again, the answer is yes. So we have a simulation now which has complexity which actually, as a function of epsilon, really saturates the lower bound that I mentioned before. It has complexity like log 1 over epsilon over log 1 over epsilon. And it's actually close to linear in t, which was, as we saw before, the best you can do as a function of t. It's a little bit worse than linear in t, but it's pretty close. So this is an exponential improvement over what we've seen so far as a function of epsilon. And the sort of details about how this works are, I think, beyond the scope of what I have time to talk about here. But essentially, what you can do is sort of directly implement the Taylor series of the evolution operator. So the evolution operator is basically the exponential of the Hamiltonian. You can write down the Taylor series of this and kind of truncate it at, somehow this Taylor series should go from 0 to k. This is the remainder term somehow that's written here. Sorry about that. But in any event, if you truncate the Taylor series to sort of the lower order terms, you don't need to keep too many terms as a function of epsilon to get an approximation which is accurate to within epsilon. And then there's a technique that we introduced which allows you to efficiently implement linear combinations of unitary operators on a quantum computer using something called oblivious amplitude amplification, which is a sort of generalization of quantum search. There are some techniques that you can bring to bear that allow you to solve this problem, which really gives you complexity, which is logarithmic in 1 over epsilon. OK. So now, as I said before, we should never be satisfied with the complexity we have. We should always try to do better, right? So what I've described so far is an algorithm that has complexity that's, so we have one algorithm that's optimal as a function of t, another one that's optimal as a function of epsilon and close to optimal as a function of t. But we would really like to have the best possible trade-off between those two and sort of simultaneously get the best possible lower bound as a function of both t and epsilon. So if you sort of combine the two lower bounds that I mentioned before, then you can see that you need an amount of time which grows at least like t plus this function of epsilon, log 1 over epsilon over log 1 over epsilon. But the best upper bound that, sort of near the best upper bound that we have is this algorithm that comes from this complexity that comes from the algorithm I mentioned on the previous slide. So it's close to linear in t and has this optimal dependence on epsilon. Okay? But this function is sort of, if you consider its joint behavior as a function of t and epsilon, can be a lot bigger than this one. So again, the question is, what can we do? Can we give a better algorithm? Or maybe we can improve the lower bound to see that actually, well, this can't really be the best we can do as a function of both, because if you just consider the dependence on t, it's really possible to achieve this t. But anyway, what we want to understand is really what is the best possible trade-off between these two parameters. OK. So some very recent work which was done by, again, people here at MIT, so Guanghao Lo, who was a graduate student in physics, and Ai Chuang, who's a faculty member here, gave a method which achieves this complexity from this lower bound. So actually, this lower bound, which is just this combination of these two lower bounds that I mentioned before, actually is achievable. There's an algorithm that has this complexity. And essentially, the way that their algorithm works is to somehow implement a linear combination of unitary operators in a different way. So what they do somehow is they encode the eigenvalues of the Hamiltonian into some two-dimensional subspace, and they somehow process the eigenvalues in that subspace using some kind of quantum control techniques, some ideas which relate to ideas like composite pulses that you might use in the control of quantum systems. OK. So again, somehow we should never be satisfied. So we've looked at the complexity as a function of t and epsilon. But maybe those are not the parameters which are most relevant to some systems that we might care about. In particular, I haven't said anything yet about sort of the number of particles in the system, kind of the size of the system in terms of how many particles there are in it. And so to think about this, let's consider a kind of simple example where we have a system of n spins that have nearest neighbor interactions. And suppose we want to just simulate it for constant time. I mean, actually, because we know how to get complexity log 1 over epsilon, somehow if we want to simulate for longer times, we can always just concatenate simulations for short times without having to worry about the growth of error. So let's just think about simulating for constant time. So if you look at the complexity of the methods that I've described so far, and you look under the hood at what the complexity actually is as a function of the number of spins, what you find is that the total number of gates you would need to give such a simulation will grow like n squared. And if you look at the depth of the circuit, which is basically like the amount of time it would take to do the simulation where you allow gates to be executed in parallel, then the complexity is linear. So the circuit depth is linear. But this is only to simulate a system for constant time, evolving just for constant time. And again, somehow systems are able to simulate their own dynamics. The amount of time it takes to evolve the system for time 1 is 1, right? So somehow the execution time of an algorithm, at least where we allow these different things to be going on in parallel, as they would in a real system, should not have to be extensive. We somehow shouldn't expect the depth of a circuit to simulate a system for constant time, at least if it's a kind of a reasonable physical system, to have to grow with the size of the system. And it turns out that, again, actually it's possible to do better. You can really give a simulation which has constant depth to do these kinds of simulations for constant time. This is some work by Ha, Hastings, Kothari, and Lowe, who now I think are all at Microsoft, but many of them were here at MIT at various times. So, again, I'm not going to sort of get into the details about how this result goes, but the kind of main kind of technical idea which makes this result fly is something called a Lieb-Robinson bound, which is a bound that describes the speed of propagation of information in quantum systems. And it basically says, there's a light cone, and information can't travel any faster than ballistically. And using this idea, they're able to develop an algorithm which is able to simulate these systems more efficiently. OK, so the last thing that I want to talk about, now that I've described a lot of sort of computational results and sort of the details of well, not all the details, but sort of the complexities of the algorithms, the best algorithms that we know for simulating quantum systems, I want to speak a little bit about the problem of making quantum simulation practical. Right? So as you may be aware, there have been a lot of exciting developments recently about trying to build quantum computers, trying to build quantum systems that would actually carry out quantum computations for many reasons, maybe to run quantum simulation algorithms, but perhaps to solve the factoring problem or other problems that we know we can solve efficiently with quantum computers. And recently there's been a lot of excitement about the kind of rapid and hopefully accelerating progress toward getting devices that will really allow us to do interesting quantum computations. So we're not there yet. We're sort of at the level where we have maybe systems of sort of tens of qubits, and maybe the quality of those qubits is not so great that we can run really long algorithms. We're not yet at the point where we have a fault-tolerant quantum computer that can run sort of arbitrarily long sequences of gates, but there's been a lot of exciting progress. So given this progress, I think a very natural question to ask is, when will we really be able to use quantum computers to solve problems that are beyond the reach of classical computers, and hopefully really use, not just sort of demonstrate the superiority of quantum computing over classical computing, but actually use quantum computers to solve problems that we care about, maybe to solve physics problems, to do things like I mentioned on some of the early slides where we perhaps simulate condensed matter systems, or maybe a bit more ambitiously, do, let's say, lattice quantum field theory. So, in trying to do this, there are definitely a lot of challenges. As I said, we're not really there yet. We certainly need to work on improving these experimental systems. When I say we, I mean people who actually know how to go into the lab and make things work. But there's a lot of work for experimentalists to do to sort of improve these systems. But I think as theorists, we should not just sort of wait until the experimentalists come back with a million qubit quantum computer that can do arbitrarily many gates. Rather, we should really think about improving algorithms to make them as efficient as possible, and also really think about how to implement them in a pretty concrete way so that we can make the best use of available quantum computing hardware. So I've described in this talk some sort of theoretical work where the focus has been on trying to improve the asymptotic running times of algorithms. What is the asymptotic complexity as a function of various parameters? But if we actually want to do this on a real device, we don't care about the asymptotic scaling. We care about what is the cost of actually doing the simulation on the maybe 100 qubit quantum computer that we have. And so we need to know which of these many algorithms that I've described so far should we actually use. Maybe the one which is best asymptotically is not really the right thing to do on a small quantum system. So one thing that some of my collaborators and I have been doing recently is to think about this question and use sort of tools for computer tools for synthesizing quantum circuits to really very carefully count the number of gates that it takes to do certain quantum simulations. And so what's plotted here are some comparisons where we look at so the problem of factoring a number which is beyond beyond our ability to factor classically, but maybe not too far beyond. So using the algorithm of Peter Shor, but these numbers that are described here come from this particular implementation that's described in a paper of Kooten. And we can look also at problems of simulating quantum chemistry. So this is a problem of simulating a molecule that's relevant to the problem of nitrogen fixation, which again is beyond our ability to simulate classically now, but maybe not too far beyond. And so in our more recent work, what we've looked at is the problem of simulating spin systems, where we think kind of already simulating systems of 50 or so spins is probably hard for a classical computer. And so what we found is that these problems of simulating simple spin systems have certainly dramatically fewer, require dramatically fewer both gates. So what's plotted here is the number of gates, specifically a certain kind of quantum gate called T gates. and also fewer qubits to solve instances that we believe are classically hard. And of course, these are only upper bounds. These are only particular implementations of algorithms that we have come up with. It's always possible to find better algorithms and perhaps move in this direction. But we've certainly identified that this problem seems like maybe a more plausible candidate for an early application of quantum computers. And we've also tried to understand which are the best algorithms that we should use. And I think maybe in light of the time, I won't sort of be able to say much about what we know about which algorithms to use. But let me just mention that some of these kind of more sophisticated algorithms that I described, it seems like they may actually be useful in early quantum simulations. So let me just conclude. I think that this area really shows kind of an interesting interplay between physics and computer science, where we've seen ideas both from computer science and physics lead to better algorithms. And ultimately, this work hopefully will lead to tools that are really useful for doing physics. There are a lot of challenges. So certainly, we want to understand how we can have faster algorithms, especially exploiting the structure of particular systems. And ultimately, though, we would like to, I think, develop practical implementations of these algorithms and hopefully use quantum computers to actually do science. Okay, thanks very much.